Hi, Steve Denenberg here. In this video, we are going to be talking about Newton's third law of motion. Here are a couple of statements of the law. The common one that you hear: for every action, there is an equal and opposite reaction. I particularly like this one. The mutual actions of two bodies are equal and directed oppositely. The mutual actions, that's going to be important. Newton also said specifically all forces occur in pairs. Now here's another way of stating it that highlights what we're going to talk about today. When an object exerts a force on a second object, that second object exerts a force on the first object that is equal in magnitude and opposite in direction. So let's take a look at a situation. You have a table and you have a block of mass m sitting on the table. Now we know that gravity is going to be pulling down on this block with a force of mg. But the block isn't moving. Why? Because there's a normal force on the block. A normal force is a force that is put on an object by a surface to constrain its motion. So if a block is sitting on the surface of the earth, on the surface of a table, its motion is constrained. It's not going to fall through the table. It's not going to accelerate toward the center of the earth with the acceleration of gravity. And the table is going to be pushing up on the block to constrain its motion like that. Normal, when you're talking about curves on charts, normal means perpendicular. Okay, so a normal force is always going to be perpendicular to the surface. If you have a block sliding down a wedge, and you'll see this is a lot, the normal force that is keeping the block from falling all the way through the wedge is perpendicular to the surface. If you have a curve somewhere, there is a tangent to the curve, and the normal to the curve at that point is perpendicular. That's why we call it a normal force. So anyway, this block is sitting at rest on the surface of the table, on the surface of the earth. Gravity's pulling down. There's a normal force that's pushing up. We know that the normal force is exactly mg because the forces must balance, equal and opposite, and it's not moving. Is this an example of Newton's third law? It is not. It is emphatically not. And you need to understand why. So here we have our block. And what are the forces on it? There's a force of mg from gravity. And there's a force of mg from the table. So the forces are balanced. But both of these forces are acting on the block. But Newton's law talks about when one object exerts a force on another object, that second object exerts the same force on the first object. And we only have one object here, so it can't be an example of Newton's law. We have accurately written out how the forces are balanced on this block, but we've shown forces that are both acting on this one block. That's object A, but we haven't found an object B yet. Now, you might say that the table, or maybe the table attached to the earth, because we're going to talk about the table and the earth as one unit, well, that's the second object. Okay, well, we'll get to that. But for right now, we're still talking about the table pushing on the block and gravity pushing on the block. We haven't talked yet about the block pushing on anything. The second problem with assigning this to Newton's third law is that the force pairs, the A and the B, that are equal and opposite, must be the same kind of force. And what does that mean? They must both be, for example, gravitational. Okay? Gravity is pulling down, but this is the normal force. That's the table pushing up on the block. There is no gravity pulling the block up. But to be a Newton's third law pair, both forces of the pair must be gravitational, or perhaps they're both contact forces. And a contact force is the normal force. The block contacts the table. The table won't let the block fall through the table, so the table is thus pushing up on the block. But gravity is pulling down on the block, so we don't have both forces being contact forces. The easy way to think about contact forces is two billiard balls knocking into each other. The billiard balls come at each other and they bang, and right when they make contact, A is putting a force on B, and B is putting the exact same force on A, and that's easy to understand. That's a contact force. Another example of a force would be an electrical force, an electrostatic force. So let's say you have a positively charged mass here and a positively charged mass here. Okay? And positive charges repel, as you will find out next year. But the force that this exerts to push this one away is the same as the force that this exerts to push this one away. So that would be a Newton's third law pair. Let's talk about the contact force again, just briefly. We said it's easy to understand when the billiard balls knock into each other. Well, the normal force that is holding the mass on the table is a contact force. And why does it happen? Let's zoom in on a little piece of the bottom of the block there. You have all these molecules that are in the bottom row or two of the block. And you have all these molecules that are in the top surface of the table. And according to something called electron degeneracy pressure, these two objects are not going to merge with each other. They're going to stay apart. When you wrap your knuckles on the table doesn't let your hand pass through. And so these molecules are knocking into each other, and that's kind of a contact force. The block is pushing down on the table, and the table is pushing up on the block. This is the normal force that we saw above. The table pushing up on the block is the force that is counteracting gravity. But we haven't really talked about this force here, where the block is pushing down on the table. The block is pushing the table down. Now, the table and the Earth don't move very much because the Earth is heavier than the block, and the Earth doesn't move very much when the block pushes on it. But it does move. And that's the Newton's third law pair, the two contact forces. We only use this force, the table pushing up on the block, to balance our forces and know if the block is going to accelerate. But the other force is actually there. Okay, we've talked about the contact force, about how in a Newton's third law pair, the block is pushing down on the table, and the table is pushing back on the block. It's these little billiard balls. Now, let's talk about what is the Newton's third law pair with the weight of gravity on the block. First of all, you can kind of tell that the contact force, like from a billiard ball, is a different kind of force from gravity. Because, for example, two billiard balls can collide with any amount of force, any amount of velocity. They can just tap each other barely with a little bit of force, or they can slam into each other with a lot of force. But gravity only pulls with exactly the force that is the mass of the object times g. So it is a different kind of force. But we have the block sitting here on the table, and gravity is pulling it down with the force of mg. What is the Newton's third law pair to that? What is the other object with the equal and opposite reaction? Well, what happens with gravity? You will learn that if you have two objects, like the sun and the earth, or any two particles, okay, there is a gravitational force between them. If this is mass 1 and this is mass 2, there is a force between these particles, and the force equals the gravitational constant times the product of the two masses over the distance between them squared. And the force goes both ways. Mass 1 pulls on mass 2, and mass 2 pulls on mass 1 with this force, okay, the product of the two. So if you have the sun here, and you have a tiny little planet out here, okay, the sun is pulling on that planet, keeping it in orbit. And the force is g, mass of the sun, mass of the planet, over r squared, where r is the distance between them. Okay, but guess what? The planet is pulling on the sun with the same force. Now, the sun isn't moving very far. The sun isn't orbiting the planet rapidly, but the planet is still pulling on the sun with the same force, because that's what the equation says. So if we have this mass sitting on the table, okay, and we know that gravity is pulling down with the force of mg, what is the equal and opposite force? Well, here's the mass, and here's the table and the earth. The mass is pulling the earth toward it with that same force mg that the earth is pulling on the mass. Now, the earth doesn't move very much because of it, but it's there. The force is there. And that is the equal and opposite force to the mg that we use to balance the forces on the mass. The earth is pulling on the mass, and the mass is pulling the earth toward it with that same force, mg. Now, the mass of the earth is much bigger than our little mass, so it's not responding very much. But that is the equal and opposite force, and we know that it happens. Now, if this stuff seems a little bit new, I have a few ways to help you understand that the contact force and the weight of gravity that we use to balance the forces and show that this mass is not moving, mg, and the normal force from contact with the table, mg, okay, are not Newton's third law pairs. Here's one way of looking at it. The weight of the mass, which is the force mg, is still there even if the block is not on the table. And if the block is not on the table, there's no contact force, there's no normal force. Well, when would that happen? Let's say that here's our table, and here's our mass, and our mass is falling toward the table, and it's still above the table. It's being pulled with the force mg. It's sustaining exactly g acceleration toward the table, okay? And the earth and the table are being pulled toward the mass. They're not moving very much, but they are being pulled toward the mass because that's how gravity works. But that's a Newton's third law pair. So here's a situation where we don't even need the contact force, and we can see that Newton's third law is applying here. So when the mass hits the table, why are we all of a sudden going to say, oh, the pull from the earth onto the mass doesn't count. Now the opposite to the gravity is the contact force. Nope, you don't get to do that. The mass's acceleration toward the earth and the earth's acceleration toward the mass are the Newton's third law pair, the equal and opposite forces. And by the way, when the mass actually does strike the table, as we'll learn when we talk about impulse, the force on the mass from the table is going to be greater than mg, because that force is going to participate in stopping the downward velocity of the mass. And so the contact force from the table onto the mass is not even going to balance the weight of the mass from gravity. Here's another way of realizing that the contact force that the table applies on the mass and the weight that gravity provides for the mass are different. Let's say you have a wedge, as you frequently will in AP Physics 1 problems, and you have a mass that is sitting on the wedge. Now, there's a force on the mass from gravity, mg. There's a normal force on the mass from the surface of the wedge. And as we know, a normal force is always perpendicular to the surface, so there's a force in this direction. Now that force has two components to it. It has a component in this direction, a component in the y direction, and a component in the x direction. Well, what's going to happen to that mass? Barring friction, that mass is going to slide down the wedge and accelerate down the wedge. It's going to move to the right, and this force to the right is going to participate in that. But it's going to move down because the vertical component of the normal force isn't big enough to match the vertical component of the force that gravity is putting on it. So mg is bigger than this force, so the wedge is going to accelerate with the downward component and with the rightward component. So look at these two. Here's mg, and this, as a side assignment, you can compute that that equals mg cosine squared of theta, if this is theta, but that's not as big as mg. So I don't see any equal and opposite forces here. It isn't an equal and opposite force, and they're completely different forces. One is contact and one is gravitational. So if you see that on a problem in the test, you'll know that they do not constitute a Newton's third law pair, and that's often how the questions will come. Are these two forces a Newton's third law pair? And I'll give you one other example, which in my mind personally really emphasizes that the two forces have to be the same type of force. Maybe it'll connect with you as well. We already said that two positive charges repel each other. Okay? And you will learn that if you have an entire plane that has let's say it has a positive charge distributed on it, if there's another positive charge above it, well, that plane is going to repel that charge. So let's say we have a plane like this, and we have a particle above it that is also positively charged. Well, gravity is going to be pulling this down because the plane is horizontal and the charge is above it. And the electrostatic force of positive versus positive is going to be pushing it up. And at some point, there's going to be some distance here where those two forces are balanced and the particle will just rest there. Well, is that an equal and opposite force? Electrostatic charges and gravity could not possibly be more different forces. Do we really think that they constitute a Newton's third law pair? What did he say? The mutual actions of two bodies are equal and directed oppositely. This is not the mutual actions of two bodies. And remember, this can't be a Newton's third law pair anyway, because what do we have? We have a floating particle. What have we done? We've balanced the forces on the particle to convince ourselves that it is at rest and it's not moving. Well, both of those forces, the gravity force and the electrostatic force, are acting on that particle. They're acting on the same object. so they can't be a Newton's third law pair. In a Newton's third law pair, the forces act in opposite directions on different objects. So to complete the circle here, the plate, the positively charged plate, is pushing up on the positively charged particle that's above it. And what is the equal and opposite force? Well, the positively charged particle is pushing down on the plate and the earth and anything that the plate is attached to, and that's the equal and opposite force. So finally, back to the block on the table one last time. When you are working problems of mass and acceleration, balance the forces. Fine. The normal force, the contact force, is mg. And we know it is because the block isn't moving, and we know that gravity is pulling down with the force mg. So the block sits. Do it. Use the forces acting on the block to predict the block's motion. But you're only looking at the forces acting on the block, and that's okay. That's how you will solve the problems. But now you know that those forces that you have balanced are not the equal and opposite forces that Newton was talking about. You don't need to show the Newton's third law pairs when you're working these problems. You don't need to think about the way that that mass is pulling up on the Earth, and that the contact forces between the bottom of the mass and the table, the mass is pushing down on the Earth with the same force, so the Earth actually doesn't move. We don't need to worry about that. We're trying to derive equations of motion, and we can ignore those other two forces. In the next video, I'll dig up a couple of sample problems that have to do with Newton's third law and show you how trivial they are once you understand this. See you next time.